Okay, I believe where we left off was going over derived units. Some more derived units, and this is not all of them by any means, but it's just kind of an overview of some of the ones we'll be dealing with fairly shortly. Another derived unit would be velocity, which is defined as distance divided by time when you're moving. The distance traveled divided by the time it took to do that. The standard unit for distance, of course, is meters, and the standard unit for time would be seconds. So the SI unit for velocity is meters per second. Another related quantity is acceleration. That is, how fast is your velocity changing? So that's divided as velocity over time. So in other words, meters per second. And when you combine the seconds, you get meters per second squared. So velocity is measured in units of meters per second squared in the SI system. Density is a measurement of how much matter is compacted into each unit of volume of a substance. And for instance, styrofoam doesn't have very much mass for each unit of volume, whereas something like lead does have a lot of mass for each unit of volume. So styrofoam has a very low density and lead has a very high density. Well, the standard unit for mass is kilograms, and the standard unit for volume is cubic meters. So kilograms per cubic meter would actually be the standard SI unit for density. Although in practice, we usually use more convenient units, but that would be the standard SI unit. Okay, so there will be many, many more derived units that we come to in the future, but we'll leave those for when we actually get to them. Looking at the basic standard SI units in a little more detail, we can look at the meter, which is the unit of length, and many other units have been used for measurements of lengths over the years. In the metric system, you also have other units like millimeters and centimeters and kilometers. But in the other measurement systems, you've got many other units of length. Some of which are familiar, like inches and feet and miles, some of which are probably not as familiar, like, say, furlongs and rods and barleycorns and things like that. So there have been a lot of different units for measurements of length over the years. Fortunately, the metric system gives us a nice logical set of units that we can relate to very easily. Because for one thing, all of the metric units are related to each other by factors of 10. That makes conversion from one unit to another in the metric system relatively easy. It's usually just a matter of moving the decimal point around rather than doing any complicated mathematical calculations like in the English system, which is not based on factors of 10. The 12 inches in a foot, 3 feet in a yard, 1,700 and some yards in a mile. I don't even remember how many, 5,280 feet in a mile. I don't even know where they came up with some of those numbers. But anyway, with the metric system, it's all factors of 10, which makes things a lot easier. A meter was originally, the metric system was developed about a little over 200 years ago in France in the years after the French Revolution, when the revolutionaries fancied themselves as hyper-rational individuals. And they tried to make everything very rational and consistent with everything else. And one of the things they did was they redid the entire measurement system and came up with what we now know as the metric system. And again, they decided that logically, it should be all based on tens, since our numbering system is based on tens, and that the quantities should be related to quantities that people were familiar with, and which were basically universally true. The inch was developed as supposedly the difference between the first knuckle in your thumb and the end of your thumb, but that obviously varies quite a bit from one person to another. So the French revolutionaries were trying to come up with units that would be the same for everybody, and they defined the meter as 1/10,000,000th of the distance from the North Pole to the equator through Paris. They were actually pretty close, and that's not bad for 200 years ago. It's not, a meter is not exactly 1/10,000,000th of that distance, but it is pretty close. Now it has been more precisely defined, and it's now defined as the distance traveled by light in a vacuum during a certain period of time. The speed of light is a constant through any given medium. That is, say, in a piece of glass, light will travel at a certain speed. In water, light will travel at a certain speed. And in vacuum, light travels at a constant speed. And the standard speed of light that we usually use, which is 3 times 10 to the 8th meters per second, or 186,000 miles per second, is the speed of light in a vacuum, which is very close to the speed of light in air. So we usually use it interchangeably as either one. Well, anyway, the distance traveled by light in a vacuum or air in 299 1 over 299,792,458 of a second. So 1/299,792,458 of a second. That's 1 meter. In terms of the English system, like I said, that's 39.37 inches, a little more than a yard. That's about 3.3 feet, or 1.1 yards. Within the metric system, 1 meter is equal to 1,000 millimeters, which is equal to 100 centimeters. Or 10 decimeters. Or 1/1000th of a kilometer. And we'll go over the metric system a little more in a little while. So that's just ways to sort of relate things. There is a table early in the first chapter in our new book here on page 12 that gives basically sizes of various things in units of meters, just to sort of give you an idea of relative magnitudes. And it goes all the way from the diameter of a proton at 10 to the minus 15 meters up to the distance to the edge of the observable universe, which is 10 to the 26th meters, which is a pretty big distance. Okay, so that's handy for comparisons of magnitudes. Okay, for mass, standard SI unit again is kilogram, and that's for mass. It's actually the mass, the standard mass is a platinum iridium alloy cylinder that's kept in the standards and measures office in France. More familiarly, it's the mass of 1 liter of water. And since it turns out that a liter and a quart are very close to each other, it would be approximately the same as the mass of 1 quart of water. That's a kilogram. It's also equal to 2.2 pounds. Okay, and let's see, it's also equal to, within the metric system, it's equal to 1,000 grams. And it's also equal to 1 million milligrams. The kilogram is unusual in that it is the one standard SI unit that already contains a metric prefix. As we'll see in a little while when we go over the metric system, the way that you change the magnitude of the unit in the metric system is to take the base unit and add a prefix to it or change the prefix. In the English system, to change the magnitude, you go to a whole different unit, like inches to feet to miles. But in the metric system, you just change the prefix, like meter to centimeter to millimeter. And in units of length, the meter is the base unit. That is, this is the unit with no prefix on it, which is sort of the standard unit. One of them would be 1 meter, and that's it. If you want a smaller unit, you can go to millimeters or centimeters. If you want a bigger unit, you can go to kilometers, but meter is the base unit. Mass is unusual in that the standard unit in the SI system is a unit that has a prefix on it. And you can, to go smaller, you can remove the prefix and go to grams, or you can put a different prefix on it and go to milligrams, and that's even smaller. But kilograms is already basically 1,000 grams. Okay, so that's mass. There is also a comparison of masses in that, oh, where'd it go? Page 12, there we go. On page 12, we have the mass of an electron at about 10 to the minus 30 kilograms. That's pretty small. And we go up to the upper limit of the mass of the known universe, which is 10 to the 53rd power kilograms. That's a lot of kilograms. Okay. So let's see. Also, I wanted to mention the difference between mass and weight. You may already be aware of this, but in case you're not, we'll emphasize it here. Mass is a measure of the quantity of matter in an object or sample. And matter is basically just stuff. Matter is anything that has volume and mass. So anything that exists physically and takes up space is matter. And so mass is just a measurement of how much matter is in an object or a sample. The crucial distance with weight is that mass is not affected by gravity. Okay, so your mass here on Earth would be the same as your mass on the moon. Okay, weight, on the other hand, is actually a downward force. And it's caused by gravity pulling on your mass. Okay, and as a result of that, weight is equal to mass times gravity, and that means that weight is affected by gravity. In the sense that weight is actually directly, the little squiggle here is the Greek letter alpha, which means proportional to. Weight is directly proportional to gravity. So if gravity doubles, your weight doubles. If you go to the moon where the gravity is 1/6 what it is here on Earth, your weight will be 1/6 what it is here on the Earth. But your mass will still be the same. It's the change in gravity that causes the change in the weight. Okay, so weight is affected by gravity, mass is not. And also, I mentioned a moment ago that Newton's second law says that force is equal to mass times acceleration. Well, actually, as we'll find out in a little bit later, gravity is actually a form of acceleration. So weight is indeed a force because weight is equal to mass times this special kind of acceleration. So mass times acceleration is a force. So yes, weight is a force. The metric unit of weight is the Newton, or capital N as a symbol. And that is, newtons are actually used for any kind of force in the metric system. So it could be a sideways force or an upward force. In the case of weight, it would happen to be a downward force. So that's a Newton. Okay, and we already said that mass is equal to kilograms, and gravity is an acceleration, which we set up here would be in units of meters per second squared. So when you multiply mass times gravity, you get units of kilograms times meters per second squared. And so they decided that this was kind of clunky. They didn't want to have to keep saying kilogram meters per second squared. So they took this unit and decided to call it a Newton. So actually a Newton really is kilogram meters per second squared. Okay, so that's it's kind of convenient how things fit together. Weight and mass. are often used interchangeably. And for instance, if you ask an American how much they weigh, they will probably give you a number in pounds. If you ask a Canadian how much they weigh, they may give you a number in pounds because they're pretty familiar with our measurement system. And if they know you're American, they'll probably give you a number that you'll understand because they're nice like that. But if you masquerade as a Canadian and ask them, they'll give you a number in kilograms, even though technically kilograms is not a unit of weight, it's a unit of mass. And so we tend to use the two terms interchangeably. We'll say, even in the laboratory, what is the weight of the sample that you put into the experiment, when what we really mean is mass. And you'll give a number in grams, which is a unit of mass. But that is, actually, it's okay as long as you're staying here on planet Earth. And in the realm of chemistry, we usually are staying here on planet Earth. But of course, physics includes astronomy, so we're not always staying on planet Earth. So we kind of have to be careful of the distinction between mass and weight in physics a little more than we do in other sciences. Because, of course, as long as we stay here on Earth, the gravity remains the same. But if we start going to the moon or Mars or anywhere else, the gravity is going to be different. Okay. So we come to time. For time, the unit is seconds. And again, the table on page 12 has a variety of times in units of seconds. We've got the mean lifetime of a very unstable nucleus at 10 to the minus 22 seconds. That is a very short length of time. Okay. And then we have some like the age of the universe, which would be about 10 to the 18th seconds, which is actually a smaller number than I would have guessed. So, okay, 10 to the 18th. Still a long time, though. Metric seconds, again, are the same as in the English system. And 1 second would be 1/60th of a minute or 1/3600th of an hour. And the second was originally devised as a certain portion of the amount of time it takes the Earth to make one complete rotation. But we've found more recently that the rotation of the Earth is not going at a completely constant speed. It speeds up and slows down a little bit from time to time. So it's now defined as the time required for a certain number of vibrations of an atom. Okay. And specifically, it's an atom of cesium-133. And 1 second is defined as the time that it takes an atom of cesium-133 to vibrate basically 9,192,631,770 times. Now, that is not something that I would expect anyone to know specifically. You should know that time in seconds is defined as a certain number of vibrations of a specific atom, but you don't really have to know how many vibrations of that atom. You should know that a meter is defined as the distance traveled by light in a certain length of time, but you don't have to know exactly what that length of time is, and so on. Okay. That brings us to the metric system, but actually I see that it's about time to end the second segment of our little lecture here. So I'm going to pick up with the metric system in the metric prefixes, specifically in the next segment. So see you in a moment.